So following on from the previous video, we got to this stage here. We got to this stage here. So remember, x is given by this function here, which is this graph here. So so this thing here represents this, and then this thing here actually represents delta t, because this is a t graph. So this thing here is delta t. The height here represents this, and then this thing here is your graph g of t. So so the height here represents delta y, and then this thing here actually represents delta t. And then we got to this stage here. So now now let's look at this graph here. I'm just going to enlarge this graph. So enlarging this graph, which will give us this thing here. So remember, this is our f of t. We are not looking at this graph. We are now looking at this graph here. Okay, so looking at this graph, that will then take us to here. Okay, so in the previous video we got to this stage here. We are now looking at this graph. So this height here represents this thing here. Okay, so hang on. So this height here is given by f of t, f of tk. F of tk is here. Remember, everything's driven in terms of time. When t, so this is our time here. This is our time. So remember, we split our time up into lots of different segments. This is k here. This is k minus 1. So this point here is f of tk, and this thing here is f of tk minus 1. So if you want to know this height, well, the height is given by f of tk minus f of tk minus 1, and that really means delta xk. That means this thing here. So remember, this height here represents this thing here, and then this thing here is actually delta t, and the height here is actually this width here, this width here. Okay, so hang on. So bear with me. So so now using the mean value theorem, if you get this height, which is this, or it can be written as this. So I'm going to jump back and forth between these two because they mean the same thing. So I would get the height. Divided by the width. That would then give us the average gradient. Well, the average gradient, well, the mean value theorem says somewhere in between here and here, there must exist a c where the derivative is equal to the average gradient. So so this is really us using the mean value theorem. So now times both sides by this thing here, that will then take us to here. So now delta xk is equal to this thing here. Now we can use the same argument for this graph. So we can use the same argument for this graph. So for this graph, delta y is given by this. Okay, so hang on, let me think. So now we can put this. Hang on, let me think. We can put this. Don't forget, this thing here is this thing here, which is delta x. So I can jump back and forth. Well, delta x here. Well, I can put this thing here into here, and then I can put this thing here into here, So so that would then take us to here. Okay. So now hang on. That would then take us to here. So now let me think. Yeah. So now it's just a matter of tidying this up now. So so if you look at this, well, what's in common here? Well, okay, let's look at it like this. Hang on. CK and then delta TK, and so you've got one block here multiplying another block, and then you've got the same, because it's squared, you've got the same thing here, and then you've got your plus here. But the point I'm trying to make here is that, hang on, dk here, and then you've got your delta t delta t. So you've got one block here and another block, and then exact same thing here because you're squaring it. Well, t squared is in common. T squared is in common, so you can actually factor out the t squared. So now, well, if you get this times this, that will then give you this thing here. If you get this times this, that will then give you this thing here. Well, think about it. From here, you can jump to here. So now, now you've got one block multiplying with another block. So root A, B, that's the same as root A times root B. So that's the same as you taking the square root of this and then taking the square root of this, which will then take us to here. And then this thing here will then become this. So hang on. So we are currently here. So remember, LK represents the diagonal length of one segment here. That's the diagonal length of one segment. So remember, A is here, B is here. This is time, by the way. We split up into lots of segments. So this LK here is a length. So this is K here. This is K minus 1. LK is talking about the length of one segment. So that's this diagonal length here. So if you want to know the whole length, you would sum up. So the whole length here is approximately you summing up all the diagonal lengths. So you summing up all the diagonal lengths will never be the same as the arc length. So that's why it's still approximately. So the whole length here is approximately you summing up all the diagonal lengths. So you summing up all the diagonal lengths. Well, all the diagonal lengths is given by, well, the one diagonal length is given by this. So put this into here. So that will then take us to here. That will then take us to here. So remember, the whole arc length, the actual arc length here, is approximately you summing up all the diagonal lengths. So this is you summing up all the diagonal lengths. Now the whole length, the whole length is now equal to you taking the limit as n tends to infinity. So if you go back to here, so remember this is A here, this is B here. So this is A here, this is B here. So when you take the limit as n tends to infinity, what you're doing is you're splitting this up into lots and lots of segments. So when n increases to infinity, this width here becomes smaller and smaller and smaller and smaller. This width here becomes smaller and smaller and smaller. So when you take the limit as n tends to infinity, this thing here, remember there exists a c. There exists a c somewhere in between here and here. There exists a c somewhere in between here and here. But then as you take the limits as n tends to infinity, the width will get smaller and smaller and smaller. So it becomes the derivative of the function itself. I hope you can follow this bit here. If you truly understand the mean value theorem, you can accept this. As n tends to infinity, the width gets smaller and smaller. C, being always trapped in between the two, well, it will lie on top of the derivative of the function. So we can jump from here to here. The same argument will go for this, and then this thing here becomes dt. So the arc length is precisely equal to you taking the integral from a to b dt. Okay, I hope you can follow that. If you don't understand why you can jump from here to here, then you need to look back at the mean value theorem. Okay.